All right, so we go to the next section here. All right. All right. So we know. So we want to. So if we have a shear if we need to so from the last section, the one thing that we need to relate is if we have an externally applied torque, how can we translate that externally applied torque into a shear flow? So in order to do that, we know that that from statics that we can say that if we look at a very small element of our section, it would have a very small contribution or torque to the total torque within the section, and that would be equal to our moment arm R from the center of the circle times the local force that would be applied at that element. Okay, so um, so if we look at that, so if we evaluate that cross product, what we end up getting is we get the perpendicular distance r perpendicular be equal to this r cosine phi term if we blew up this triangle times the shear stress at that point tau of s times the thickness t of s times d of s. Okay, so so that gives us an equation to relate our shear our torque and our shear stress along the side of the beam. Sorry, the side of the tube. So we can again remember that the shear flow is equal to tau s times ts. So we can substitute that in to this equation here, and we can get the answer. All right. So so if we then integrate tau along the length or the perimeter of the section, we can and I guess the thing that we should remember is that Q is constant along the beam, so along the section, so we can bring it outside our integral. All right, and then if we integrate R of S, D of S, what that ends up being is just equal to 2 times our area. Okay. So, all right. So now we have an equation that relates our torque and Q, right, and our torque and our average shear stress along the section. So the last thing we need to do is we can say that our shear stress at any point along the perimeter would be equal to the torque divided by 2 times the mean perimeter of the tube times T of S. So the torque within a section is a constant. The area is constant. So the only thing that might vary is the thickness. So if you have a thicker section, you'd have a lower shear stress. If you have a thicker section, you'd have a smaller shear stress. So so this relationship states that the shear stress is going to be inversely proportional to the thickness. All right. So so if we plug in the values for a circle, you would get this equation for the shear stress. So all we're doing here is plugging in A is going to be equal to pi r squared here. All right, that's all. All right. All right. All right. So, are there any questions regarding the relationship between between the shear flow and the applied torque somehow? Y is the result of the integral to A. Um, I believe it has something to do with um, um, the. I believe it has something to do with this. Yes, I believe what it I believe what it is. It is the integral of the. So the question for those who are online was, why is the integral of r of s ds equal to 2a? And I believe what it has to do is you can substitute this ds term in here. So this is for this element. We can relate ds to dA by saying ds would be equal to 2 dA over r cosine phi. So and then we have r perpendicular s is equal to r perpendicular of s is equal to r cosine phi. So the r cosine phi's will cancel each other out, and we're left with 2 dA. And if we integrate that, we would just get 2 times the area. Does that make sense somehow? Okay. Yeah. So that's where that came from.